Hello students, in this video I am going to explain dimensional analysis. That is, what do we understand by the term dimension of a physical quantity? Here I will discuss its applications and limitations. Also, 4 numerical are explained for practice. Let us start the video. Dimension of a physical quantity are parts to which the base quantities are raised to represent that quantity. There are 7 base quantities. They are length, mass, time, current, temperature, luminous intensity and amount of the substance. The dimensional formula is the expression which shows how and which of the base quantities represent the dimension of a physical quantity. For example, volume can be expressed as length into breadth into height, which can be written as L cube. Similarly, force is mass into acceleration and it can be written as mass into units of acceleration, that is mLt minus 2. Frequency is 1 upon time period. So, it can be written as t raised to the power minus 1. Similarly, work done is force multiplied by distance. Force we have just calculated and distance is expressed as L. So, it will be mL square t minus 2. Strain is change in dimension upon original dimension. Both are length only, so it is a dimensionless quantity. The dimensional equation is an equation obtained by equating a physical quantity with its dimensional formula. Like we have just written the dimensional formula of volume, that is L cube. So, if we write that L cube on the right hand side in square brackets and on the left hand side the notation for volume, here I have taken as V in square brackets is written. It is termed as a dimensional equation. Similarly, I have written the dimensional equation of frequency. So, notation of frequency I have taken as F in square brackets and on the right hand side its dimensional formula, that is t raised to the power minus 1, both m and l quantities raised to the power 0. Similarly, for the work done. Now, principle of homogeneity of dimensions. All terms of any physical relation must have the same dimensions. That is, whenever we are writing a dimensional equation, the left hand side dimensions of all the quantities, that is m, l, t, should be same as the right hand side. Likewise, I have taken an example here that mass m raised to the power a is on the left hand side and on the right hand side it is mass raised to the power x. So, this equation is dimensionally correct when a is equal to x. Similarly, when b is equal to y and when c is equal to z, the principle of homogeneity is followed. Applications of dimensional analysis. The first application is checking the consistency of the equations. That is, to test the consistency of equations, we have to find the dimensions of left hand side and right hand side of the equation. And if both the dimensions are same, that is the equation is dimensionally correct. That is same as the principle of homogeneity. Now, deducing relations among physical quantities. This is the second application. If we have to find the relationship connecting a physical quantity to a product of its dependence quantities, then the dimensional analysis can be used as a tool to find this relationship. Third application is conversion of units. This method is useful in finding the conversion factor for changing the units from one set to a different set of base quantities. That is, if we want to change the unit from SI to CGS, then also dimensional analysis method can be used. Limitations of dimensional analysis. It supplies no information about the dimensionless constants. They have to be determined either by the experiment or by the mathematical investigations. Also, this method is applicable only in the case of power functions. It fails in the case of exponential and trigonometric relations. It fails to derive a relation which contains two or more than two quantities of like nature. That is, if the expression consists of summation or subtraction of two quantities, then also this method fails. It cannot be used if the physical quantity is dependent on more than three variables. And it can only check whether a physical relation is dimensionally correct or not, but it cannot tell whether the relation is absolutely correct or not. Let us solve numerical. Test the dimensional homogeneity of the following two equations. The first equation is h is equal to h naught plus v naught t plus half gt square, where all the terms are having their usual meanings. H is height, so it is expressed as length. H naught, that is the initial height, is also expressed as length. V naught is initial velocity and t is time, so it is expressed as velocity into time. L t minus 1 into t, that is L. And half gt square is expressed as g into t square, where g is acceleration due to gravity, which is L t raised to the power minus 2 and t square. So it will also lead to L. So if you view carefully, the left hand side and the right hand side terms are all having the same dimensions. So the above equation is dimensionally correct. Let us see the second equation. Second equation, the left hand side is K. K stands for kinetic energy. The kinetic energy dimension is ml square t minus 2. And on the right hand side, we are having half mv square plus ma. Half mv square is m stands for mass and v is the velocity. So if we calculate its dimensions, it will come out to be ml square t minus 2. And the last term is m into a, that is mass into acceleration. Again, if we calculate its dimensions, it is mlt minus 2. But this dimension is not same as the left hand side dimension of kinetic energy. So if we view carefully, the left hand side and right hand side dimensions are not same, and hence the above equation is dimensionally wrong. Second numerical. The time of oscillation T of a small drop of liquid under surface tension depends upon the density rho, radius r and surface tension sigma. Find the dimensional formula of time of oscillation T. That is, T is proportional to density, radius and surface tension. So we have marked here as density raised to the power A, radius raised to the power B and surface tension raised to the power C. So if we remove the proportionality sign, there will be a constant K. Let us mark it as equation number 1. Now we are writing the dimensions of both the sides of equation number 1. T is time, so it is written as in square brackets capital T. Rho is density, so density is mass upon volume, so it can be written as ml raised to the power minus 3 and A will be written as it is. Radius is length only and surface tension is mt raised to the power minus 2. Let us combine the right hand side terms. Here it is m raised to the power A, then is m raised to the power c. So let us combine, it will become m raised to the power a plus c. Similarly, L raised to the power minus 3a plus b and t raised to the power minus 2c. Comparing the powers of m, L and t on both the sides of the above equation, we find that a plus c is equal to 0. Minus 3a plus b is equal to 0 and minus 2c is equal to 1. Now Let us solve equation 2, 3 and 4. After solving, we have obtained A as 1 by 2, B as 3 by 2 and C as minus of 1 by 2. Putting down all these values A, B and C in equation number 1, we have obtained this relation. Just after the simplification, we can write down the time of oscillation relationship. It will be K times under root rho r cube upon sigma. Third numerical. A large fluid star oscillates in space under the influence of its own gravitational field. Using dimensional analysis for the expression for its period t of oscillation in terms of radius of the star, density of the fluid and universal gravitational constant. That means here the time period of oscillation depends upon radius, density and gravitational constant g. Removing the proportionality sign, there will be a constant k. Let us mark it as equation number 1. Now again writing the dimensions on both the sides. This is time t, so it will be written as t raised to the power 1. On the right hand side, that is radius is length, density is mass upon volume and universal gravitational constant is m raised to the power minus 1 L cube and t raised to the power minus 2. Adding the powers of m, L and t on the right hand side and equating with the left hand side, we have obtained these equations. That is b minus c is equal to 0, a minus 3b plus 3c is equal to 0 and minus 2c equal to 1. Solving these equations, we have obtained a is equal to 0, b is equal to minus 1 by 2 and c equal to minus 1 by 2. Putting down the values in equation number 1, we have obtained this relationship, that is t is equal to under root 1 upon rho g. Now let us solve last question. The SI unit of force is Newton and the CGS unit is dyne. By the method of conversion of units, we have to find out how many dynes is equal to 1 Newton. The dimensional formula of force is mLT minus 2, and when we are writing in terms of newtons, the SI unit of mass is kg, SI unit of length is meter and SI unit of time is seconds. And when we are writing in terms of dyne, the force can be expressed as 1 gram into 1 centimeter into 1 second raised to the power minus 2. Now dividing the above two equations, we have obtained this equation. If we simplify it, we have obtained as 10 raised to the power 5. That is 1 Newton is equal to 10 raised to the power 5 dynes. That means by the method of conversion of units, we have converted 1 Newton in terms of dynes. Thanks for watching. Please like, share and subscribe.